Integers and strictly parametric if every base b between 2 and n minus 2. What it means? Given an integer return to if n is strictly parametric. Okay, every base between n. I want to know what is the n's range. Okay, it's very big. So, okay. Okay, so okay, simulate it. Try to simulate it. Go right here, and the girls for each base should be in 2 and minus 2. Right, so try to simulate it. Okay, so for zero at value mode, the base. Okay, that's it. Given about the index numbers, it's ready to separate of length to width equals sum. Note that the two separate must be at a different index. Alright, so okay. So idea, use hash table, hash set to recode length to sum. size, and use insert. If we insert and that's it. Wait, this two has the same sound. Okay, that's it. Maximum rows covered by columns. You given about zero-based binary math and columns versus numbers of rows you must choose. Rows cover a set of columns. Each row has one lies on the columns. Choose a set. What means maximum numbers of rows can be covered by a set of columns. Maximum cover. What is a row is covered by a set of columns if each cell of a row has value 1 less than 1 column. Choose a set. What it means? It means that what it's you given about the columns, you know the numbers column, you must choose. Okay, you must choose. Okay, so we may choose 2 columns, and then if we choose 2 columns, we will only these 2 columns here, and then that can be covered by set. This can be covered, this can be covered, this can be covered. Okay, so it can cover 3. Okay, so okay, I think okay, it's very small, so the constraint is very small. So we can use backtracking. That size is columns. Right, so idea it's backtracking. Alright, so let's say we can use choose column will be what is this math? Okay, this column it's going to be minus, and test. Can use boolean because so if choose column, if choose column, we say right, so if math is going to be choose, and if choose column J is going to be false. Can break. Right, so we can use OK. Okay, so DFS. We can either skip it. Choose it. So skip will say I plus 1. And what I choose it? Choose it will say that it's right, that's it. Okay, you given robots, and you given to index numbers arrays, charge times and running codes. What it means? The i's running codes are charge times you need to charge, and codes and running codes you need to run. What is this? I don't understand. Harmony statement is a little long. And okay. And robots. And you given two integer arrays, say charge time and the running cost. Both are less than. And the i's running cost charge time you need to charge. Oh, okay. So it counts this unit to charge, and it counts this unit to run. Alright, so budget. What is the budget? The total cost of running K. if we choose that robots is equal to maximum charge time at the case sum running cost, where the maximum charge time is the largest charging cost, total cost of running case. Largest charging cost among K robots and some cost max number of consecutive robots you can run such that the total cost does not exceed budget. Just see this line. Maximum number of consecutive robots you can run such that the maximum total cost does not exceed. So total cost does not exceed the budget. So first find the consecutive robots such that smaller budget. Alright, and then what should we do here? If we're total cost of running K choosing robots, K choosing robots is equal to maximum charge time. So we just care this total cost of this function. So what is the total cost? Say if we choose 3, it is possible to run all individual and consecutive pairs of robots within budget. Now what about obtain the answer? Consider the first 3. We'll get that the maximum charge time is going to be 6, and the running cost is going to be 3. Sum of 6 is 18. So right. So actually just these functions here. The maximum charge time should be smaller than budget. Right, we just care these functions. So and we need to be consecutive here. So so this can be the single. If we choose K, sync running cost and maximum. So if we choose this case, we don't know the K, right? So we don't know the K. We just find out that must be consecutive, right? So basically this sum of the values should be minimum and the sum of the maxima should be minimum, right? This maximum is going to be 6. The sum of the value is going to be 12. Alright, so I have an idea. It's binary search. Binary search K, because given a K, if 3 consecutive robots can satisfy these functions. Does not exist. So does not exist is not equal or equal. So it's not equal. because okay, so maximum is right. We can binary search the answers. Now given our answers, we just sliding window. Okay, sliding window the coast map. Right, so given the check, even the window is already okay here. We're now saying that it's going to be true if can window size is budget. Cows smaller in budget. Right, so let's say we can use another set and we insert about the charge times of I, and the sum of this is going to be running cows so if base case is that if state maximize R begin here and add about k times sum is more in the budget. Right, so let's slide window here from K and say insert about charge time and the sum set will erase here. Right, this is check functions. Now we are going to be insert 0. So if check, it means we can guess more window. Right, that's the idea. Wait. What? Why runtime errors here? Is this case gets 3, right? So another case we say we cannot choose anything, say 0. So now that the case going to be 0 if tree always can be choose. True. Alright. Alright, so too slow. Seriously. Why? Okay, so this case is right, so need to be optimization because the current time capacity is going to be here. Alright, so it's a large constant, right? Alright, so okay. Can use the Q, monotonic Q here. Okay, this is monotonic Q, mass Q. So if push the I, but basically we maintain a mass heap decreasing. So while dq back charging time here is too small. And then this is a mass mark Q, right? And now so if charging time still be here. And the front, it's still here. Front is the maximum value. Okay. Push back. This can reduce to n linear. Okay, so it's kind of right, so it's a little tight. Alright, it's a little tight. Seriously. This is too slow. I just said surprised about this. I see the problem through. Wow, it's a little tight. Alright. Well, that's it. Okay. Waste 10 minutes. Okay, so just alright, so just care for the using the queue that's so fast because this overhead is a large constant in this problem. Say it's going to be NLK. Sometimes it's NLK here, and then in total kind complexity, so we need to binary search. So say login. Well, I don't understand why this will be time limit. Is it because the constraints rect is smaller, right? So okay, but yeah, doesn't matter. Just okay, doesn't matter. Alright. Okay. Get to penalty. Yes. Dimaster. Okay. Well, let's see the problem. So this problem a little tricky, but I almost overthink in this problem because the length two subarrays equals sum, and they cannot be begin at a different they must be the begin at different index, right? So this problem we only care about we only need to find the length 2. So what is the idea? We can brute force or subarray that length 2, right? And but we need to handle the subarray beginning same index. So what should we do here? So we can use a hash table to over hash state to record the subarray of length 2, and then we just like a sliding window length 2. So in this window we check out the sum as a 6 because when we move it, we also move the left right position, so we can generate to the problem to determine if there is a 2 subarray length k with the equal sum. We can be general to this problem. So yeah, so the idea is that we can just try to use a hash state, and then we just compute the sum of the subarray because and then putting the hash table, check that the hash table is this value, and when we move forward to next index, the start position never be equal. So we can generate that the sum of the maximum subarray can be satisfied when we find the equal sum here. The subarray must be different. Yeah. So here I'll use a hash state. So the overall kind complexity is going to be linear, and the space kind complexity is going to be linear. Alright, so yeah. And what is this second? Insert, we will return about what? Return the first is the iterator, and the second is the is successful insert into the set or not. So it's success or not. So if we insert it, let's say not success or not, it means that it means if it has success insert to the set or not. So if we cannot success insert into this subarray sum, that means we have already appeared the same subarray sum. So that's the idea, and we found it, return true. Okay. And problem 2. Okay, so this problem we just find out that it's determine that if the integer n is strictly palindromic if every base between 2 and n minus 2 is in this base is palindromic. So for example, it's 9, we have 2 to 7, base 2 to base 7. We just check for each base. We need to check that, okay, is this the palindromic? If this is a palindromic, if this is a palindromic. If yes, let's say yes, the palindromic. So return true. So what is the idea? Actually, we can just the brute force, right? So this problem just brute force. We just try every base from 2 to n minus 2. From 2 to n minus 2 brute force here. And then what is the time complexity here? So in the first group, that will take linear. And this, how many numbers operation? At most log 2 here, because why is log 2? Because it's like log 3. Actually, it's log 2 at log 3 and blah blah blah. But we can we can say its upper bound is this. So it's n log n here. Yeah, so n log n here. So yeah, so that looks well and can pass the constraint here. So now this check function is also be linear, but it's also be all log n. Log n here. Log n here. Okay, this is just brute force check that the palindromic is just let's say it really send forward and backwards. So we just reverse string and then compare string. If let's just send is a palindromic here. So if we just try every base here, if the string is going to be we want to convert to the base b here, and then we just try to so what is the current digit here? We just add a multiple value, and we don't care about the base 2. What it means, I mean, I don't care about this value is reversed, because for example, say 4 in 4, actually the binary the 2 base is going to be 1 0, but in this situation we'll get 0, 0, 1, but doesn't matter. Because we want to check. We don't need original. We don't need the real base number. We just calculate. We just need to check that it's the perigeny, and that doesn't matter if we reverse the string. So yeah, that's it. Alright, so that's problem 2. Problem 3. Okay, so that's my final rank. Actually, I think waste too much time to submit. Okay, let's just okay, this problem is very boring. I don't like this problem because actually there is nothing. It's similar to previous context, Actually, it's like okay, let's just take go through the problem statement. It's that you're given the matrix, and then you're given the integer columns. You need to find out that the set of columns such that it's not a set of columns. You can determine a set of columns here, and then you need to find out that what is the maximum numbers of a row that can be covered. What means cover? Cover means that a row can be satisfied in the chosen set. For example, if we choose this column. So if we choose these 2 columns here, then this row can be satisfied because this is empty, this is empty, this is empty, and this is 1 is yes in the chosen set. This is 1 yes in the chosen set, and this is 1 is not in the chosen set, so this row cannot be covered. So the maximum number of rows is 3. So what is the idea? Actually, we just backtracking because why we can backtracking because the constraint is really small. So okay, what is the kind complexity? So it's 12, right? So it's 12, but actually it's not that. Actually, it's not really that not really as this number because it's the combination. The combination is going to be, for example, the maximum is going to be 12, right? So we want to choose the columns. So actually it's choose the columns here, where this is the combination. So actually the bottleneck is this. Bottleneck is upper bound. Largest number is going to be this. Actually this value is very small. Okay, so we just generate or possible here, and then we just for each column we can choose it because we want to choose a subset. So we go through let's see this code here. So this DFS function is going to be choose for each column. We have 2 operations here. We can either choose the columns or not choose it. So so we can choose the column. We choose the column remain will -1, or we can skip last column, and until we reach the last column, reach the depth, because we cannot do anything. We just check that okay, if it remains 0, that means that we have choose the columns. columns. Yeah. Okay, so now is the problem is that how do we check? It's actually very simple. We just we use the choose column. You know what I mean. This is the column we choose, and we just go through the matrix and just check that. Okay, so is the column is the 1. If this matrix is 1, and if this is we don't choose the column, that means that we fail. So yeah, so I just add how many numbers of a row we are success. Okay, so that's it. Okay, I forgot to calculate the operations here. So worst case is mn times this C and choose columns here. Okay, yeah, that's it. Not really big. And this problem, well, actually a lot of people get tiny means it because I think the constraint is a little tight, but it doesn't matter. But you just use actually I think you must use the optimized solutions to solve it. Okay, so the proper statement I think is a little ambiguous because these two lines have no use, just no use. You just see the last line, return the maximum number of consecutive robots you can run, such as the cost does not exceed the budget. And you just need to know what is the cost in here. The cost in here is that is this function, the maximum charge time we choose, and the sum of the running cost times k. Yeah, that's it. So what is the idea? Because in example 1 we say we choose 1 can be satisfied, we choose 2 can be satisfied, we choose 3 can be satisfied. So actually we just binary search the k, the number of the chosen robots. We just binary search this value. Why? Because if 3 robots can satisfy this budget, that means that the 2 robots can always be satisfied from a condition because 3 is satisfied. There is no reason that the 1 or 2 will fail because yes, obviously. Yes, so we just binary search the k, the robot we choose. And now what is the problem? It's that determine you given about the row you choose. What is the smallest cost here? Or we don't care smallest. We just check that if this function can smaller than the budget. So in here we just slide window. So now let's see the sliding window part here. So given about the window size, we want to determine that okay, so if the cost can be smaller than the budget, smaller or equal to the budget. So in this function, the time complexity will be linear. Okay, let me export it. Export. Okay, let me demonstrate it because we can sliding window. In this running code is very simple, right? We just maintain a window and we add the value, we minus the value. But the hard part is maintain a maximum window sum. Maximum window. That's the maximum window. We can use the monotonic decreasing queue. So it's another problem. Okay, I just maintain the monotonic decreasing queue. So the first value in the queue is the maximum value in this window. So in this line, we are popping from the back. If this value is too small, we pop out because we never use this value here. We can pop out this. because we always can use I to determine because I can cover this back, right? Because this is greater in this window, I is the maximum, then I is greater than this value, so I can be covered the back. We can pop out this. So yeah, so that's the reason this thing. And what about this? So just try. Okay, the code is a little duplicate here because we push back this, pop out this. So we can merge. Okay, we can merge this code to generate more clean here. So yeah, no we can pop out this. So and then so if I is greater than k, if I is more than this. Alright, that's not important. Let's just see this code. In this window we just pop out, we just maintain a monotonic decreasing Q, and then after we get this, we also have a window. And now let's just move the window. So we move the window. And this sounds very simple, right? We just add that, right? So we add that and minus the value we don't use in this window. And then we also pop out this. If the maximum value is too far than the distance is too far than the k, we must pop it from, because this maximum is no use, and this is the same as the previous concession. Here is maintain the maximum here. So that's the idea. Yeah, so dq here. Yeah, that's the idea. So this check function will be linear, and then we binary search the k is also is log k here. So total k encompasses is log n. Actually, it's log n here, right? So yeah, that's it. If we search is good, that means that this answer is it can be determined. It can be used. So we search a greater value and update the answers. Okay, the answers is increasing. We don't need to do this because the answers is increasing. Yeah, because we search the right side here. Okay, so that's the idea. Okay. Right, so okay, so that's my final rank. Right, so thanks for watching.